You're on the Argmin video channel on Real Analysis, Lecture 23, More on Continuous Functions and Introduction to Normed Vector Spaces, or NVS. Alright, so getting right to it, we had a theorem from the last lecture that we proved. Recall IVT, which says if f from the closed interval a to b mapping to R is continuous and z is a real number such that f of a less than or equal to, or to strict equality, less than z, less than fb, then there exists C in AB such that f of z, f of C is equal to z. Okay, and we saw that proof last lecture, so the corollary to that is if f mapping the interval AB to the real numbers is continuous, then the image of the interval AB under F is itself a closed interval. Closed interval. Let's prove this. So suppose f is a function mapping this interval and it's continuous. Now let's look at f a b. Since f is continuous at a b, which is compact, then the image itself must be compact. So by the extreme value theorem, m is equal to infimum AB, and take m equals the supremum of AB. Oops. That would be boring. That would just be m equals a and big M equals b. AB and f a b exists, and there must be an x and y in that interval such that f of x is equal to m and f of y is equal to big M. So we claim that AB passed through F is the interval small m to big M. So by construction, we have that f of a, b is contained in M, big M. Now we show the other containment. Take some z in that interval. If z equals m, then z equals f of x, and if z equals big M, then z equals fy, and moreover, if m is less than z less than big M, then f of x is less than z is less than f of y. Then by the intermediate value theorem, there's some constant c in that open interval in the middle of a and b such that f of c equals z. So it must be that f of a p is itself a superset of the interval m to m. So we have that z is in there. And finally, closing statement, f a b is equal to that closed interval. So that is a closed interval as required. Okay. And let me just double check something about this proof. Takes out in z equals m, then z equals fx, then z equals big M, then z equals fy. So in here, when we were trying to prove that continuous functions map closed intervals, we had that f of x less than z less than f of y. If x is less than y, we automatically have z equals f of c for some c in xy by the IVT. But what if y is less than x? And let me just move that down. So this is assuming x less than y. If y is less than x, we can just negate everything. Negative fy less than negative z less than negative fx. And since negative f is also continuous by the properties we looked at, there exists some c in yx such that negative f of c is equal to negative z, so fc equals z as required. So that gives us this c, so then we can include this part. Okay. Let me just rearrange this proof. This, oops, that's too much. This can move down there. And then this part, just for better exposition, can go down there. And let's just make everything nice. Okay, so If a continuous function, it maps closed intervals to another closed interval based on the extreme value theorem, and we proved it using the intermediate value theorem. Okay, let's talk about paths. Let A be a subset of Rn, and let A and B in a path in A from A to B is a continuous function given by gamma, mapping AB to A such that alpha 0, or gamma 0, sorry, is A and gamma 1 is B. So we have this gamma 0, 1 to A, and so you have this interval A to B. If you pass that through your function gamma, then that gives you some arbitrary path between 2 points. A and B. Let's call that 0 and 1. And this is gamma 0. This is gamma 1. And in between is gamma varying from 0 to 1. Okay? It's a path. Proposition. Let A a subset of Rn, and suppose F from A to R is continuous if there is a path from A to B in A such that F of A less than Z less than F of B, then there exists a point C on the path such that F of C is equal to Z. And here's a proof. Suppose F mapping A to the real numbers is continuous, and let gamma from the closed interval from 0 to 1 to A be a continuous path such that gamma 0 equals A and gamma 1 is equal to B. Now consider their composition. Mapping 0, 1 to R, which is also continuous by a composition property we looked at before. So since F of A less than Z less than F of alpha B, that would mean that F of gamma 0 less than Z less than F of gamma 1. Just from substitution, just cleaning up my gammas again and again until it looks nice. Or readable, not nearly nice, but readable. So by the intermediate value theorem, there must be an A in the open interval such that F of gamma A is equal to Z, and so take C equals alpha or gamma. Gamma. Oh crap. We already defined A. Did we? Yeah, we did. So let that be an alpha. C equals gamma alpha. And we're done. So there's a point such that FC is equal to Z. Alright, that's about it for continuous functions. Now let's move on to our next topic on normed vector spaces. Or NVS for short. Okay, let's define what we just used up there. Let V be a vector space over the real numbers. A norm on V is a function looking like that from the vector space to some non-negative number. So some properties it must satisfy are that don't like the overlap. Norm of x equals 0 if and only if x equals 0 to alpha x. That norm, you can just take the alpha out for any x and v and alpha real number. And property 3, if you take x plus y, that norm, it must satisfy the triangle inequality. And that's usually the interesting property. The rest are pretty straightforward. So we defined what a norm was. And so we call the pair V and the norm a normed vector space. Okay. So for example, if we take V and Rn, then the 2 norm is just the norm we've been using this whole time, which goes from I equals 1 to n of xi squared, and then the square root. You can have a different norm on the same vector space, which satisfies the properties of being a norm. x1, x2, to xn. This is called the one norm. And it's just the sum of the absolute values of each coordinate of the vector. Let me write that so it's a bit less clear. There's too many vertical bars. And as another norm, we mentioned it a couple of times, but here it is. The infinity norm, xn, subscript infinity, is the max. It's really bad. For value I in 1 up to n. Of the absolute value of each coordinate. So it's the largest magnitude coordinate. As an example, we say that for a compact subset of Rn k, V is equal to Ck is equal to F mapping K to a real number such that F is, use a bar there, continuous. Then it would be that F plus G x equals Fx plus Gx. So this is the space of functions now. This is a new definition for us. So this is a set of functions which map a compact subset of the real numbers to a real number of the real vectors, sorry. Compact subset of the real vectors, K subset of Rn to a real number, so F is continuous. And that satisfies this, since F is continuous. Then the uniform norm is written as an infinity norm, and instead of a max, it's a supremum, and instead of a x being discrete, or the optimization variable, it is now over the entire domain. And it's just an extension of the infinity norm from Rn to a continuous function space. As a remark, F is continuous and K is compact. The supremum of F of K must be less than infinity because of compactness. So it follows it's uniformly continuous. So then the supremum must exist. So F infinity is defined the uniform norm only when K is compact. So let's highlight uniform norm as well, because that's a new term. As an example, let's take the vector space C, A, B, and P from 1 to infinity, and this is called the LPAB norm, written as F subscript P is the integral from A to B, the absolute value of f of x raised to the power of P integrated over the variable x to the power of 1 over P. So we looked at some more properties of continuous functions, defined what a path was, then looked at normed vector spaces and gave a lot of examples on normed vector spaces, particularly for the vector spaces being Rn and the space of continuous functions mapping compact subsets of Rn to a real number, which has a norm, uniform norm, and also if the vector space is a continuous function from the closed interval giving us the LP norm. And that's it for this lecture.